Hello, so this is our next lecture about previously we have discussed circular and rotational motion. Now we'll discuss a bit different topic. It's called fluids or fluid mechanics. So we have to begin with states of matter, and basic three states of matter. These are solids, liquids, and gases. So ideal solids, they don't change their shape. They don't change their shape, cannot be stretched, bent, or compressed. So they don't change their shape. Now liquids and gases. They are called fluids because they can flow. So fluids can be compressed or expanded, compressed and expanded. Both liquids and gases. Liquids have definite volumes, but no definite shapes. So they have definite volumes, so that's why they're similar to solids, but they have no definite shape. They take the shape of the container. Gases have no definite volumes, no definite shapes. They can expand to fill large containers, or they can be compressed to fill small containers. They can escape the open containers. So these are the main properties, and differences between these three. They arise from strength of forces between molecules. So in solids there is the strength of the forces between molecules are strong. So we can write strong. In liquids they are weaker. In gases they are the weakest. Compared to solids and liquids. So atoms are closest in solids, the closest to each other. Here they are further away from each other, and here the other take the longest. There are biggest distances between atoms, so attractive for this, and this is because of attractive forces that they have the weakest in gases. Solids, because the atoms are close, they are the densest. These are not that denser solids, and these are have the lowest densities in gases. And because solids, they are dense, they are hard. Here atoms are not that close as in solids and liquids, and therefore they can flow, they can atoms are free, they can flow. Liquids take the shapes of the containers, and gases, the forces are weak, so they are free to move. So another thing that is important to us, it is a quantity, physical quantity, mass density. Mass density is defined as mass divided by volume. So the units are kilograms divided by units of volume, whether it depends on the units that you measure, but usually it is kilograms in meters in the third degree in superscript. So solids have the highest mass density, and because the atoms are closest to each other. Now pressure, another quantity, very important physical quantity, it's pressure. So pressure is force divided by area, force divided by the area. If force is applied, if we have, and the units are newtons in square meter, it's called Pascal. So if the force, if we have some kind of surface area, let's say circular, and we have the force that is applied to this surface area, so we divide the surface area, we divide the force by surface area, and we know the force and we know the pressure. So force divided by surface area is pressure, and if the bigger force is distributed over a smaller area, then pressure is higher. In gas pressure, so pressure in gas, if we have a box with gas molecules, because there are a lot of gas molecules in the box, they are moving randomly, and because they have temperature higher than 0 kelvins, they have kinetic energy. due to temperature, and they are in constant random motion, and they constantly collide with the walls of the box. So they are hitting the box. They have kinetic energy associated to speed, so they are randomly moving because there are a lot of molecules. We can speak about average pressure of gas to the walls of the container. If we increase the temperature, they start moving. If we increase the temperature, they start moving even faster. And the pressure exerted on the walls increases. Liquid pressure. So liquid pressure, liquids, they cannot support themselves as compared to solids. So that's why because of this they are in containers. So if we, let's say, imagine that we had a liquid, it is, let's say, not in a container, just imaginary situation. So this is the container, let's say this is the liquid, and let's imagine that liquids are in some kind of layers. That liquid is distributed in some kind of layers. So these layers cannot support themselves. So these layers, let's say this layer slips down to this side, this part of the upper layer slips down to this side. They cannot produce sidewise forces to support themselves. So that's why this structure collapses, and these layers, they fall down, collapse, and that's why we don't have this shape of water that the same that is in the container, and therefore this whole structure collapses, and we have only the water on some kind of surface. And each of this layer, it has because of the gravity, it exerts a weight on this lower layer. So this layer that I've just colored exerts a weight on this layer. This layer exerts a weight on the layer that is below, and therefore there is a weight. And as you can see on this layer, 1, 2, third layer, there are 2 layers above, so the weight increases. So the weight increases as compared to, because the weight of these layers sum up, and the weight on this layer, the one that is closer to the ground, consists of all the weights of all these layers. So the weight adds up, and therefore, as you go deeper into the water, into the pool or into the sea, you feel this pressure, and this pressure increases. So this pressure is called hydrostatic pressure, and if you have outside the container you have just, let's say at this point you have atmospheric pressure, the pressure that is because of the Earth's atmosphere. Earth's atmosphere is attracted to Earth's atmosphere is attracted. How to show this? That you have gases everywhere, and this is the atmosphere. Earth's atmosphere has a mass, and this because gravity attracts this atmosphere everywhere. You know, atmosphere is everywhere around the Earth, so gravity attracts this mass. So it produces the weight on the surface. So F is ma, m atmosphere, and m contributes to atmosphere, and therefore the surface and everything on the surface of the ground, it experiences the weight. Surface of the Earth, and every object, human beings, trees, everything, and objects, they experience the weight of atmosphere. This is called, this weight divided by surface area would be pressure, atmospheric pressure. So therefore atmospheric pressure is the same everywhere, and because gases and liquids, they in gases and liquid, pressure is the same in every direction. Therefore atmospheric pressure is the same everywhere. So we can talk about atmospheric pressure here, here, and here, and also here, here, and here. So in every point there is atmospheric pressure. But inside this container, let's say at the height h, so there is also atmospheric pressure at the height h. So there is atmospheric pressure, and we can speak about force. So force is P atmospheric times surface area, because force divided by surface area was pressure. Pressure was force divided by surface area, so we can write force like this. And also there is what? There is a, in this point there is a weight of this water. We may increase the amount of water, so there is a weight of the water above, so this water is pulled down, and the forces on this point, so there are force due to atmospheric pressure, and also the weight of this layer of water, of this mass of water. So it is given by by what? By the force of gravity. So it would be mass times g of this layer of water, mass of this layer of water times g, and we can write that this is the net force. So F net would be F atmosphere plus F gravity or weight. In this case, it would be better to write weight. So what's happening now? We can express this F net as P atmospheric times surface area. Surface area may be better to write A, capital A. Capital A. Now we can write that mass is what? Mass is density times volume times g. Yes, this is mass. Volume is what? Volume is surface area times the height. Times the height. So now this height corresponds to this. Let's write maybe this capital H. This height would be capital H. At height this, so the height would correspond to this. Small h correspond to the layer of water, this layer of water, and surface area would correspond to this container, to this surface area of the container, because it would be the same for this amount of water. Now we can write that net force is instead of volume, we can write A times H, G. And now we can divide by everything by surface area. So we would get this net pressure. Pressure divided by surface area would be pressure. Force divided by surface area would be pressure. And here we divide this part by surface area, which has the where it is multiplication by surface area. So we get atmospheric pressure plus this density rho and H and G. So this is called hydrostatic pressure. So this hydrostatic pressure it depends on height, and it depends on height. So if you have the layer of water that has some kind of height, so if you have height, this small h, the height of this water, so then the pressure at some kind of point below this water would be given as rho, h, and g. Okay, so now it was hydrostatic pressure, and what is important that pressure in liquids and gases is transmitted to, let's say we have some kind of object here. So pressure in the liquids and gases, it is transmitted to all directions equally. So if there is pressure, so it is, let it be, let's say it should better be a small object, some kind of small object. So we can neglect the changes in the height. So the pressure comes here, the pressure comes here, the pressure comes here, so it's transmitted to all directions equally. So the pressure goes to the walls, it is transmitted equally. Also, hydrostatic pressure depends on the height. So here would be a higher pressure because of the height, because there would be higher amount of water at this point, at these points. This would be bigger pressure than compared to here, because the layer of water is thin here, so the pressure is low. Here the pressure it increases because the layer of water becomes thicker, and the thickest layer of water with the highest pressure is down at these places, because it is all the liquid inside the container. So now the other thing is Pascal's principle. It says that, basically says the same thing that I said you now, that pressure is transmitted undiminished to all points in the liquid. So it means that pressure is transmitted undiminished to all points in the liquid. So this is applied, so it means that P1 is equal to P2. So this is applied in hydraulic systems. So we can write this F1 divided by S1, F2 divided by S2. So, sorry, surface area. Surface area, and if we have some kind of hydraulic system, let's say, and there is, let's say, a piston here that can move up and down, and it is S1, it is A1 area, surface area A1. This is and the force applied down is to this A1. To this A1 we apply the force F1, and what happens, there is a pressure P1. So this is area 1, yes? The piston having area 1 surface area. So we have P1 now. Through this liquid, that is liquid inside, we have a large piston here, which has surface area A2, large surface area, and therefore the pressure, the force, because the force is the same, P2 is the same as P1, so the force is the same, therefore pressure is the same, therefore the force has to be also the same, so F2 should be the same. And if we have a big object here, let's write a big object, so then it just gets pushed up. So this is how hydraulic systems work. Pressure is, force is small, area is small, pressure is P1, but because P1 is equal to P2 here, that where area is big, so therefore force has to be big. Now there is Archimedes principle, and Archimedes principle is dealing with buoyancy, the force of buoyancy, and if you have a cube that is immersed in water, so there are forces on this cube, so forces to the sides, side walls, forces from up, from the water above, forces from, this is due to water pressure, forces from the water below to this front wall also, and to this back wall, to this back wall also. And as you can imagine, these all forces, because of the pressure of water, and the pressure of water comes from the weight of the water, so these forces, they side forces, they cancel out. This force cancels this force out, so the net force is 0. So this force and this force. Now this force that comes to the front and to the back sides, they also cancel out each other. Now these forces are remaining, so F, this is F top, this is F bottom. Do they cancel each other out? Basically no, because F bottom minus F top, it is, so this, let's call F net force. So F bottom and F top, what happens? At the top there is thinner layer of water, so that is thinner layer of water, so at the top, but you can see from the bottom all this layer red, so this F top is produced only by this red. F bottom is produced by what? It is produced by all this and all this red. You see what happens? So the force at the top, this bottom force, F bottom is higher than F top. It is higher than it is higher, so also there is what? There is gravity pulling down on this object. So there is also the force of gravity. So if we have the center of this object, there is gravity force pulling this object down. So F bottom minus F top minus F gravity. So this F net is then produced by, this is called F buoyant force minus F gravity. So buoyant force is F bottom minus F top. So this buoyant force is always up. F buoyant is always up, so it pushes the object up. If the object is in the water, so it pushes the object up. Gravity pushes the object down. Pushes the object down. And what happens? And that happens if the buoyant force is higher than is equal to gravity. Then the object, as you know, it can be at rest. There is no force. Net force is 0. So then the object can be at rest or can move with a constant speed in a straight line. So therefore, in the water, this object can flow in at any position, at any depth. If other cases, if F buoyant is higher than F gravity, the object will float on the surface. So this means floats at any depth. So if in this case it floats on the surface, if less than F gravity, then it will sink. The object sinks. So basically, Archimedes' principle says that the object is tends to displace the volume of water if you put the object inside the water. Let's say the immersed object tends to displace the amount of water, the volume of water that it has, the volume that it is equal to object's volume. So it tends to displace it, and the water, the displaced water, so it tends to displace, so the water increases. Yes, when you immerse this, the water was in this point, then the water does what? The water tends to increase. Let's say to this point. So let's say maybe it's bigger object, let it be bigger object. So the water is displaced to this point. So the initial was here, so the water level rises. When you go into the bed, the water level rises. So the water is displaced, and the water wants to, let's imagine, wants to go down and pull this object up. So this is the principle. So if that volume of water is enough to make the object float, so then the object floats, and we can write that this buoyancy force it can be written in the terms of these forces. So we can write that it is the density of water. So we can the density of water in terms of hydrostatic pressure. So this would be G, and this would be volume of the object. So this force is called buoyant force, and depends on water, G, and volume object. So here comes the volume of the object into play. If you put into the water chunk of some kind of metal, then it will drown. But if this chunk of metal takes the shape of a higher volume,